Let us now consider one-dimensional example of the finite element method. We are using the space capital V equal to the subler space W0, 1, 2, and we are considering the following Dirichlet problem. This is the strong formulation of it, and you know what the weak formulation of this problem is. For simplicity, we only choose omega equal to the interval from 0 to 3, and let us consider the example where you have some rod of length 3 and with 0 boundary conditions. So we know that the temperature is 0 here and here in the boundary. So our boundary is only 2 points in the one-dimensional case. And inside here we have some source F, some heat source, and for simplicity let us just consider the following triangulations. There, in the two-dimensional case we had the triangles, the interior of triangles. In this case we only can use intervals. So omega, this omega is divided into this triangulation. From 0 to 1 is one interval, from 1 to 2 second interval, and the third interval from 2 to 3. So here is the weak formulation of the problem. We want to find the solution U such that A of U V is equal to L of V for all V element in the subler space W0. So here we have just replaced this phi by V, but it does not matter what symbol we use. So in this case, in the one-dimensional case, we want to replace this space W0, which is infinite dimensional space, infinite dimensional space, with a finite dimensional space. And let us show you what these are. First, note that the bilinear form A of uv is given by this integral as usual, but in this case the interval, we only use the interval from 0 to 3, so omega is from the interval from 0 to 3, and the integral here is just replaced by from 0 to 3 here. It's a usual integral on the real line. Moreover, this L of v, the linear form, is given by this expression as usual, and instead of using omega here, we can use this integral. Instead of using this more complicated integral over omega, we can use this integral instead. So let us now show what kind of basic functions we are using in the finite dimensional space. So here we see the solution U. This is the solution of our problem, and we want to approximate the solution with the finite element solution UH. So this UH is element of the finite dimensional space VH, which in this case is only a two-dimensional space, because we are using these kind of basis functions. So in our triangulation we had these three intervals, and the only way we can use linear functions on or functions which are continuous and at the same time linear on each of these intervals in the triangulation are these two functions. So we have this v1, which has its top point at 1, and this has the top point, the maximum point at 2. Moreover, we will, as an example, use the following source. F is a constant function from 0 to 2. It's defined as 1 in this area, and it's going to be 0 in the rest from 2 to 3. So this is given in our task. For simplicity, we choose that the conductivity is equal to 1 in all cases, in the whole interval, for all x. So, using the general theory, we know that our problem is now to find this un element in the space V is not un but uh in the space VH, such that this equation is or this identity is satisfied for all V in this finite element space. And since we are only using two basis functions, any function in this space is of this form: v1 multiplied with some constant real number xi1 plus v2 xi2. And as we learned in the previous lecture, the problem we are going to solve is the following. We have this matrix equation A xi equal to B, where B is this vector, xi is this vector, and A is this matrix. So what we need to find is these elements. We want to find the elements of the matrix A and the elements of the two elements of the vector on the right hand side B. So we know the bilinear form, and let's start with finding the value of A, v1, v1. We take the integral from over omega, which is from 0 to 3, and this interval is too large in some sense to integrate, so we have to split this integral into 3 integrals and add these integrals. One integral from 0 to 1, another from 1 to 2, and a third from 2 to 3. So we know that lambda is 1 in all the intervals. So let's put this in here. Moreover, the derivative of the basis function v1 with respect to x is equal to 1 in this first interval from 0 to 1. Let's go back and show you that this is so. The basis function v1 is this basis function, so from 0 to 1, the derivative of this function is just the slope here. So its derivative is only the height here divided to this length, which is 1. In this area, v1 is equal to minus 1. And in this interval, v1 is constant, so the derivative is equal to 0. v2, on the other hand, is opposite. So it's 0. The derivative of v2 with respect to x is 0 in this interval, it's 1 in this interval, and minus 1 from 2 to 3. So let's now go back and write this here. In this interval we used that derivative of v1 was equal to 1, and of course it's the same here because it's the same quantity. So 1, 1 here in this interval from 1 to 2, we saw that the derivative was minus 1. So we write minus 1 there, minus 1 there. Just replace these guys with minus 1 and minus 1. And in the last interval, the derivative, as we saw, was equal to 0 because it was constant. The basis function was constant in this interval. So we write 0, 0 here.